Good day, everyone. We are Group 5, and today we present our project for WQD7004 Programming for Data Science. Our project title is Applying Decision Tree and Random Forest for Predicting Exercise, Angina, and Resting Blood Pressure. On behalf of my team members, Yuhan, Yuqi, Xingxi, Shed, and myself, Leonal, thank you for being here. Here is our agenda for today. We will start with the business understanding and our objective. Then we will walk you through our data understanding, preparation, and modeling process. Finally, we will present our evaluation, conclusion, and idea for the future. First, let's talk about the problem. Cardiovascular diseases are the leading cause of death globally. As you can see from the charts, these numbers are rising. In 2019, they represent 32% of all deaths worldwide. This is a serious issue, and early prediction can save life. This is the main motivation for our project. Our main objective is to use machine learning to predict the risk of heart disease based on patient data. For this project, we focus on two specific tasks. First, a classification task to predict if a patient will experience exercise-induced angina. Second, a regression task to predict a patient's resting blood pressure.
Thank you, Leo. Now let's look at the data. We use the heart failure prediction dataset from Kaggle. As you can see in the table, our raw dataset has 918 patient records and 12 attributes. The data includes patient demographics, like an average age of 53.5 years, and is mostly male. Importantly, we found that 55% of patients in this dataset had heart disease, and there were missing values in the resting blood pressure and cholesterol columns, which we needed to address. So next slide. So for data preparation, to get the data ready for modeling, we followed several key steps. First, we standardized all column names to make them easier to work with. Second, we checked for missing values. We found that some zero values for blood pressure and cholesterol were not possible, so we replaced them with an A to mark them as missing. Then we imputed or filled in these missing values using the median value for each gender group. After that, we converted all categorical columns like gender and chest pain type into factors so the model can understand them. Finally, we check for duplicate data and analyze outliers, but we decided to keep the outliers because they could represent real clinical significant cases. Next slide, EDA. So next we perform EDA, exploratory data analysis, to find patterns. On this slide, you can see several distribution. The age of patients is normally distributed, peaking in the 50s. We also confirm the data is mostly male. A key finding is that the most common chest pain type is SY, which is asymptomatic. This is important because it shows that many patients have no symptom, which makes a predictive model more valuable or very valuable. So on next slide, slide 8, we look at correlation. The heat map and pair plot show that there are no strong correlation between most of our predictors variables. This is good because it means our features are independent, which helps to build a more stable model. We did note some visible outliers in cholesterol and old peak, which we were mindful of during modeling. So next is modeling.
Okay, thank you, SYED. Now we move to modeling. Our first test was classification, where we had to predict exercise include angina, a yes or no answer. As you can see in the workflow, we split our data with 80% for training and 20% for testing. We used two models like logical regression and random forest. To evaluate them, we use the accuracy, AUC, and the confinement matrix. Next slide, please. Okay, here are the results. The table shows that both models perform very well. The logical regression models had an accuracy of 77.6% and an AUC of 0.853. The ROC curve on the left visually confirms that both models are much better than random guessing. On the right, the valuable important plot from our random forest model shows us which features are the most important for making prediction. The key features was old peak, chest pain type, max 𝗖𝗄/ST sloped. This is a great result because these are no clinic indicator for heart screening. Okay, next. Our second test are regression to predict the exact number for a patient's resting blood pressures. Our first models, linear regression and SVR, showed very low R squared value, which means they are not very predictive. The plot shows the prediction was quite scarce. This told us that we need to optimize our approach. Okay.
Okay. Thanks, Chloe. To improve our regression model, we perform optimization. This includes selecting the most relevant features and using techniques like grid search for the SVR model. After testing, our optimized model performed better. The SVR model gave us the highest R-square value at 0.119, while the optimized linear regression had the lowest error or RMSE. Overall, the improvements were small, which tell us that predicting blood pressure is a very difficult task with this dataset. Next slide, please. To summarize our evaluation for classification, both models were very good, with AUC scores over 0.884. This means we can reliably predict an angina risk. For regression, the performance was much weaker. Even our best models had a low R-squared value of around 0.1. This suggests that the features in our dataset do not have a strong influence on resting blood pressure, and more data is likely needed. And thank you.
Next slide is the conclusion. In conclusion, our project had two very different outcomes. We found that we can predict exercise-included angina with high accuracy using models like logistic regression and random forest. Our models confirm that clinically relevant variables are the most important predictors. However, predicting resting blood pressure is a very much more complex problem. Our models showed only a weak relationship, and we believe this is because our factors like lifestyle or medication, which were not in our data sets, are more influential. The next slide. Of course, our project has some limitations. The dataset was small and lacked key information like smoking history or medication use. Also, it was a cross-sectional dataset, meaning it was a snapshot in time. For future work, we recommend using larger, more diverse data sets. We could also explore more advanced machine learning algorithms and most importantly, validate our models on internal data to ensure they are useful in a real clinic setting. Okay, the next slide. Thank you.
This brings us to the end of our presentations. Thank you for your time and attention. That is all for us. Thank you.